The name of this video is the Irrotational Property of E. As it turns out, the irrotational property of E is the second Maxwell's equation for the electrostatic field that we are going to encounter in this course. So obviously, it is very important. In order to introduce the rotational property, let us begin with a more generic field, vector field. And so let's define a vector field A vector, and let's hypothesize that such a field is characterized by a central spherical symmetry. So we want this field to be a central field, and in addition we want it to have a spherical symmetry. So in math, what does it mean to have a vector field A which is central and with a spherical symmetry? In math, this simply means that A vector can be rewritten as a function with a magnitude f of r. We don't know this functional dependence, but the thing we know is that this function depends only on if we, for example, if we consider an origin here, let's do it here. If we consider an origin O, okay, and for example, we consider a spherical coordinate system. So in a spherical coordinate system, let's say this one is r, the radial axis, and of course we are considering a spherical coordinate system. So in general, we would have O, R, bar phi, Z. But if the magnitude of this vector field is a function only of R, not of bar phi and Z, only of R, then this is said to be a central field, okay? And in order to have a spherical symmetry, we also want to have only one vector component of this field, which is UR, okay? So if the vector field has only one direction, UR, the radial direction, and in addition to that, the magnitude of the field is a function at this point in time unknown, a generic function f of r, only of r, not of r phi and z, okay, then this is a vector field A with a central vector field A with a spherical symmetry. Okay, so these are the key ingredients to make such a field. Okay, and again, f of r is a generic function. At this point in time, we don't know what it is. So if we look at the field lines, let's say like the Faraday field lines of this vector field, central vector field with spherical symmetry, then, for example, one line could be exactly this one. This is one line of the field. This could be another line of the field. This could be another line of the field. It has to be central, and also remember that this representation is a two-dimensional representation of the vector field A, okay? So I'm only doing this representation on the plane of the board. Of course, it's a three-dimensional field, so you can rotate it around to understand what it looks like in 3D. And let's pick one more line. For example, this line here. So these are all vector lines, okay? So let's put also the vector. So these are Faraday lines for this vector field. They all stem from the origin here, O, and they all go outside, directed as UR, which is the only component. There is no phi component, there is no Z component. Okay, so now in this configuration, let's consider a closed line. So the closed line is going to be A, B, C, D back to A. So for example, let's say that this is point A. So we go from A, and let's hypothesize that this arc belongs to a circle which has O as the origin, okay? So this is a circle, let me continue here, with origin in O, here. Okay, so then we continue from B, which is this point here, we go up, let's say to this point C, then from C, we go over an arc which is parallel to the arc AB, so this arc will be like this. So it's parallel because again it belongs to a circle which again has O as a center, so CD, and then back to A. So this has to be an oriented line, so it goes in this direction from A to B, from B to C, from C on the arc to D, and from D on this line back to A. So this is our closed line gamma oriented from A, B, C, D back to A. Okay? And again, A, B, and C, D are arcs with center in O. So a very simple closed line. Let's begin with a simple one. Okay, so under these conditions, we want to compute the line integral along this closed line gamma of A dot TDL. That is, we want to compute the circulation of this central vector field with spherical symmetry. Okay, this integral can be split into 4 integrals, from A to B, from B to C, from C to D, and from D to A. And so let's look at them one by one. So we're going to have the integral from A to B. Okay, let's give a few definitions here. So this distance is RB, which is the same as RA, and this distance is RC, which is the same as RD. Okay, so let's write it down here. The radial distance R A from O to A is the same as RB from O to B. Similarly, the radial distance from O to C, RC, is the same as the radial distance RD, obviously, because these are arcs with center in O. Okay, so when we do the integral from A to B, let's in this case, let's just write on the A to B arc, okay? So here is quite simple, the integral, and why is that? Because we know that the tangent unit vector here, T, of the TDL, in this spherical coordinate system, is nothing but U bar phi. Okay, it goes along the phi direction. So remember, this is R, and this is our bar phi, okay? So, whereas the field A, in this case, is directed as UR, because it's a central field, directed as UR. So obviously, when we do here, F of R times U of R, which is our vector field, dotted with U bar phi, obviously, this we need to do it, obviously the infinitesimal element, so let's write it one time here. So the infinitesimal element along this line A to B is U phi is the direction, and then we need to have RA or RB times D bar phi, okay? So this is the infinitesimal unit element dl. So TDL is U phi, which is T, and dl is the radius times the angle, okay? So that's our TDL right here. Let me circle it. This is TDL. All right. So obviously, this integral gives 0 because we are doing the dot product of 2 normal unit vectors. Okay. What about the integral? So let's do plus the integral from B to C. So in this case, we need to integrate from RB, which is the same as RA. So from RA to RC, okay, of F of R, UR, dotted, in this case, the unit vector here is obviously UR, and so we just need to do dot it with with the UR and this is the unit vector in the R direction, so times dr. So TDL in this case is UR dr, okay? You are the arc. Excellent. So obviously this quantity gives me 1 in this case. Good, what about the integral on the arc CD? Well, on the arc CD, okay, like this, we are performing the same integral as the first one, so we have f r u r dotted with u phi, r in this case c d bar phi, and this again gives us 0 because u r and u phi are orthogonal to each other. And finally, we have plus the line integral from RC, which is the same as RD. We are going from D to A, so RC and RD are the same, even though I'm going from D to A, RC is the same as RD, back to A, which is RA. Okay, so we are going the opposite. Here we went from RA to RC, here from RC to RA, of f of r, u of r, dotted with again. Okay, here actually, I wanted you to think for a minute about this. This is a typical mistake that we all do, as a matter of fact. So what is the mistake we all do? Typically, here, students tell me, and actually this was what I thought as a student the first time, okay, now we're going from D to A, so we are going opposite of the art direction. So when we do times dot TDL, so we think that here, TDL should be minus UR dr. Is this actually true? Well, as it turns out, it is absolutely not. So this sign is wrong. And why is that? And note that we are going from RC to RA, and RC, which is the same as RD, is larger than RA, okay? Because of this very reason, so we are going from something larger to something smaller, whereas here we are going from smaller to larger. So this minus sign is already encoded in the limits of integration, which in this coordinate system go from large to small. So if you already have this information in your integral, you go from large to small, you don't have also to flip the sign of TDL because you're already accounting for that sign in the limits of integration. On the contrary, if you were saying I go from A to D, so I invert these limits, then I need to account for the fact that I'm walking in this direction into the differential TDL. But since I'm going from C to A, then the minus sign, it would be redundant and it would be wrong. Okay, so it would be redundant. So you would have two minus signs which cancel each other. So whereas here, instead of having a minus, we keep having again a plus UR dr. Okay? This is actually quite nice because we can flip these limits of integration, changing this sign. So we put a minus sign here. And here we go from, we can always use this property of the integral. So we go from RA to RC, okay? And so by doing so, we know that here we have plus the integral from RA to RC of this quantity, which is exactly the same as the integrand here. The only difference is that here we have the integral minus from RA to RC. And so obviously, these two integrals cancel each other, so that the final result of this line integral, of the circulation, is exactly 0, as we wanted to show here. So in this case, we can say that for this specific closed line, the circulation is 0. Okay. Does it mean, and note that this little trick of the minus sign is actually very important. Many people do mistakes, so please try to remember that. Let me actually highlight it in yellow, okay? So this is connected with this integration here. Okay. So, now, is this sufficient to state that such a central field is actually an irrotational field? Well, obviously not. We need to generalize this concept, and this is what we are about to do. So, we want to extend this proof which we have done for this kind of field for a very simple closed line to any generic line. So suppose to have a line which looks like, let's also do it in orange like we've done here. So let's say that the line looks something like this. Okay, this is our closed line gamma, okay? Where, again, I remind you that we had our particle our center of all of the coordinate system, O, somewhere down here. Okay, so this is our radial coordinate system. R, good. Now this is a very generic line, much more complicated than that. So let us focus only on a very specific region of this line. So let us zoom in, for example, let us zoom in this region of space here. So for example, let's consider, we can extend, the idea is to extend this concept to this line, but to begin with, let's consider only this line here. So the line I'm about to consider, it goes from here to here, from here to here, and back. Okay, so let us zoom in this region. So if we do so, we will find out that this line looks very much like this line here. But in this case, to generalize the concept, I'm assuming that this angle here is an infinitesimal angle d bar phi, okay? So it's a very small aperture, which therefore results in very small arcs, which can be approximated as if they were, since they are part of an infinitesimal angle, belonging to two circles with center in O, okay? So that's the idea. All right, so if we do that, let's zoom in. So we find eventually that this line will look like this. Okay, where again, these two circles, these two arcs, belong to two circles which are with center in O. All right. So let's further split this line into two sublines. Okay, we can do that, where each of these angles will be d bar phi divided by 2 if you want. And so let's say that this is point A. So from A we go in this direction to point B. From point B in this direction to point C. From point C in this direction to point D. And from D back to A in this direction. Okay, so this is our line gamma prime, which is equal to A, B, C, D, back to A. All right, what about the other line? We go from, in this case, from D, we go, let me do this with a different color, so it's clear what's happening here. Let's do this in green. So the other line will be from D to C in this direction, from C to this point, let's call it A, B, C, D, E, in this direction. From E, we go to this point F in this direction, and from F, we go back to D in this direction, okay? So this line, we call it gamma double prime, and is equal to D, C, E, F, D. All right. Great, so now we have this overall line here, which stems from an infinitesimal arc with the angle d bar phi. Okay, now here I just zoomed in and I further split it into two sublines, where again, so it's basically doing this. So we just split it and we have this other line like this. Okay, so alpha of the line is this. So gamma prime and gamma double prime. All right, great. So now with that in hand, the next thing we want to do, we know that the line integral for a vector field with central spherical symmetry over this line gamma prime has to be 0, because this line gamma prime is exactly the same type of structure as the line gamma we have here. The only difference that again is generated by an angle d bar phi divided by 2, but it's the same shape, okay? So these are arcs, concentric arcs with center in O. So obviously the line integral has to be 0, which means the line integral on a closed line gamma prime of A dot TDL, and again later I will skip A dot TDL because it's always the same, this has to be equal to 0. In addition, it turns out that obviously also the line integral on gamma double prime has to be equal to 0, because the line gamma double prime is also very similar to gamma prime and very similar to gamma. It's actually the same kind of line. So now we can sum up these two integrals, okay? If each of them has to be 0, also their sum has to be 0. Okay? Now, we know from the properties of integral that we can recombine these two lines. And what happens if we combine them? So what happens if we do gamma prime union gamma double prime, so that we can shrink this and make it a single integral? Well, this would be, let's look at this carefully. So we go from A to B, BC, and as from DA as well. So DA, AB, and BC belong solely to line gamma prime. Similarly, CE, EF, and FD only belong to line gamma double prime. But this line, DC, belongs to both, and we walk over this line in one time in this direction and one time in this direction. So we go in this direction for gamma prime, and we go in the opposite direction for gamma double prime, which means this line here effectively doesn't count when we do this union. And so the union of these two lines effectively is from A to B to E to F back to A. Okay? So we obtain this bigger line here. Okay? And so this means that this integral, we can simply write it as the line integral on this super line, which we call just gamma. And this has to be equal to 0. This is actually great, because now we can repeat this argument for all these possible angles here, for any angle, until we span eventually the entire line that we are considering here, gamma. So we go from this point to this point, and we span the whole line. Eventually, at the end, it's just a point, okay? The line shrinks down to, these lines shrink down to a point. If I sum them up with this concept in mind, I obtain always that the lines separating adjacent closed line of this type cancel out, don't contribute, and so the overall integral has to be 0, which means the line integral over the entire line gamma, which is what I already done down here, has to give us 0. Okay, so this means that any central vector field with spherical symmetry, like A, has to be an irrotational field, okay? So A is irrotational, which also means it's conservative in a simply connected domain. All right, so what we want to do next is we want to specialize ourselves to a special case. We want to consider a special case of a special central vector field with spherical symmetry. And what is such a special field? The electric field. We already know a special type of central vector field with spherical symmetry. What is that? The electrostatic field E. In fact, the electrostatic field E from Coulomb's law for a single point-like charged particle in space is given by 1 over 4 pi epsilon naught times q divided by r squared. This quantity here is nothing but f of r in our generic definition of the field A. So now we know the functional dependence with respect to the variable r is 1 over r squared with these pre-constants, with these prefactors. Right, so now we know that, so it's a specific case of this type of field, and the direction in a spherical coordinate system is only along UR, so similarly to the A field here. So this, the electrostatic field E, according to Coulomb's law, is a central vector field with spherical symmetry. This implies that the circulation along gamma of E dot TDL is equal to 0 for each line gamma in space, anywhere in space, okay? So this, which I'm about to circle here in yellow, is the irrotational property of the electrostatic field E, and this is nothing but the second Maxwell equation in statics in integral form. Okay, so this is quite amazing. In a couple of videos, we already were able to prove and write down two fundamental laws of electromagnetism, which are the first two Maxwell's equations for the electrostatic field. The first was Gauss's theorem, and the second is the irrotational property of the electrostatic field, right there. All right. Not that many people underestimate the importance of the irrotational property, but actually the irrotational property is more important, if you want, than Gauss's theorem. And so I will come back to this in a few videos. All right. So this is actually quite interesting, because it also means that the electrostatic field is a state function. Perhaps you took also courses in thermodynamics. So, and as I said earlier in a few videos ago, this means that if I take the line integral between 2 points, capital M and capital N, of the electrostatic field E, the integration is independent of the line which I follow. I could choose a straight line, like this gamma double prime, a very complicated line like this, like gamma triple prime. All these line integrals are exactly the same. And of course I'm integrating always E dot TdL. So this means that these integrals depend only on M and N, but not on the way I get there, only on the limits of integration. Okay, also another thing which is worth discussing briefly here is the concept of one of these line integrals. So what happens if I multiply one of these line integrals by, let's say, the charge Q naught, which is our test charge, which is spanning the three-dimensional space? Well, this quantity, Q naught times E, is nothing but the force, the electrostatic force F, and so this is nothing but the work due to the electrostatic field E along line gamma. So this is the physical meaning of these line integrals. They're nothing but the work of the electrostatic field, okay? Performed by the electrostatic field. So in particular, if my particle Q naught is here on this line, from B to C, this particle will follow these lines, and so in this region we say that the particle falls along the field lines, is folding along the field lines. Okay, if I leave it there, it goes in this direction. Whereas from D to A, that's not the case. In this case, the particle is rising, so rises along the field lines. And in fact, here I need to apply an external force that counteracts the electrostatic force in order to make it move in this direction. Okay, but the interesting thing is that the work along this closed line gamma here is, for example, in this case, 0. Note that this concept here can be extended readily to the case of discrete charge distributions with, for example, n point-like particle in space, as well as continuous charge distributions with, for example, density rho or sigma, etc. And how do we do this? Of course, as always, by means of the superposition principle.